Okay, I'm gonna start sharing my screen and take it for the point we left it last class, which is we're talking about the principal component analysis. And remember, we said that for key principal component analysis to have to be able to apply principal component analysis, we need some sort of correlation among the different variables. Let me see, I have to admit more people here. Let me see, more people to admit. Hold on. No, that's it. Okay. Let's see if we can actually start. Okay, so we one of the assumptions we made is that there has to be certain level of correlation between the different variables. Remember, all variables are treated equal here. There's no response variable. Okay, so this is, for example, the data from the Swiss bank notes. And if you remember, we have measurements on the Swiss bank notes that measure the length of the note, the height on the left side of a note, the height on the right side, the inner to lower dimension, how much, what's the measurement between the inner to lower frames, the inner to upper, and the diagonal, okay? Now, to analyze, in this case, there are a few variables. This is the correlation matrix of the variables. We can review the numbers and see if there's any variable that has zero correlation or very small correlation with all of the other variables. But it's easier to see, particularly when we have more variables, it's easier to see it in a graph, okay? So if we see it in a graph, I guess there's nobody else to admit now. Oops. Okay, so it's easier to see it in it's easy to see to analyze these correlations in a graph, and that's a graph. We'll be generating these graphs later when we start working with the R script. Now, here what we need to look at is, as you know, the color of the block indicates how strong the correlation is. The darker on the blue side or the darker in the red side, the stronger the correlation between these variables. So we can only review if there is one, if we found one variable that had very light squares showing very small correlation in absolute value with all of the others, for example, this one has very low correlation with the length, right? This is the inner to upper, and the correlation with length is small. It's on the light gray side, but however, it has stronger correlations with this variable, which is left height and the right height. So there will have to be a variable that has little blank squares, almost blank squares, for all the other variables, okay? And that we could remove that variable from the analysis because it's not going to add any value in a principal component analysis because there's no correlation with any of the other variables. But so this is an easier way to do it, to see it. This is another way that we can analyze how the different plots, the different variables behave. And again, this can be done for a reasonably small number of variables. If you have 800 factors or 800 predictors, which happens in practice, or even less than that, let's suppose you have 100 predictors. And having a 100 by 100 plot showing the scattered diagrams, and this shows, for example, this is the density, the estimation for the variable, okay? This is the density estimation also here for the left height and so on. So we have the individual distributions, see how they behave. And we also have the correlation if of each of the variable with the other variables. For example, we have here the correlation between left height and length is 0.238. Okay, the correlation between right height and length is equal to 0.152. Okay, so we can see the correlations, and we also see the scatter plot. For example, here we can see that in this case that I'm pointing here with the mouse, there seems to be a positive correlation, right, between those two variables, which is the length height and the length, right? Length height and length. So that correlation is about 0.743, which is positive because we're seeing it in the graph. And we see other interesting phenomena here. We see, for example, in the diagonal, we can see a bimodal distribution for the diagonal data. And you can appreciate that here in these two groups. There seems to be two groups with the diagonal data. So there's a lot of things you can see from this type of chart. If you're trying to assess correlation, a more useful chart is the one we saw earlier, because that's just color-based, and it's very easy to distinguish if there's a variable that has almost zero correlation with all the other variables, which you can also see here, but have to read the numbers. Okay. And again, if we have here, we have only 2, 4, 6 variables. If we had 15 variables, the graph is going to be much better. The previous graph is going to be much better to interpret, much easier to interpret. Now we're going to be doing this thing in R in a few moments, but there's a function that we'll be using to extract the eigenvalues. And what this function is going to give us is the eigenvalue. If we have 6 variables, we have 6 eigenvalues, right? Because we'll have 6 principal components. These eigenvalues are ordered in terms of the variance that they represent from the total set of original data. So this tells us that the first eigenvalue is such that the corresponding eigenvector is explaining about 66.75% of the variability in the data. So that's a big chunk of variability that's being explained. And in the last column here, we see the accumulative sum of these numbers here. So for example, the first one represents 66.75, and the cumulative sum is the same because it's the first component. The second one explains, yes? Could you mute your mic unless you want to ask a question, please?
Which was the third column?
The third column is the cumulative sum of the second column. Okay, so what this tells us is the first component, this is the first one, so it's only adding this one, is 66.75%. The first 2 components explain 87% of the variability, the first 2 components. Okay, so that's what this thing is saying, that the first component explains 66, and the first 2 explain is 87%, 87.5, and the first 3 components explain 92% of the variance, okay, that we have in the original data. They're always printed from the highest to the lowest, because that will correspond to the first principal component. This will correspond to the second principal component, and so on. Okay. Now, when an eigenvalue is greater than 1, it indicates that the corresponding the eigenvector is explaining more than a single variable of the original variables. Remember, the principal components analysis, all it does is makes a transformation of the original variables to try to transform it in such a way that most of the variance is explained by the first component, the second to most is explained by the second component, and so on. So if an eigenvalue is greater than 1, it means that it explains more than one variable of the original variables. If it's less than 1, it assumes that this is saying that in the second eigenvalues is 0.93. So this one is explaining less variance than a single of the original variables. Okay. Sometimes the criteria that some software packages like SPSS have for as a default is that they will only consider eigenvalues greater than 1. That's a default, but you can always change it. It will depend on several factors here. It will depend on how important it is to explain at least X percentage of the variance in the data. Sometimes the criteria is I want to keep the principal components so that I explain at least 90% of the variability in my original data. Then we would have to go with 3 components. Or we could say, well, that's close enough to the 90%. We'll go with the 2 principal components to analyze that data.
I have a question.
Yes.
How do I like establish this criteria?
It depends on the problem you're trying to solve.
Okay.
In most of it, what you always want is a very small number of principal components. That's what you want.
So
And when you have variables that have very low correlation with the others, that's gonna distort this thing, and you'll need a lot of components to explain a large percentage of the variance. Normally, it's useful to have 2 components or 3 components at most for for example, we're doing regression with the principal components. But it depends on how much variance they explain. If the first 3 components only explain 60% of the variance, maybe that's too low. We need to go one further. Okay. There's a device we're going to be using, which is called the script plot, and that will help us determine how many components you should use. Okay.
okay.
This is, for example, a chart of the component 1 versus component 2. Okay, these are the first component and the second component. That's a scatter plot. We can see 2 groups. We know that this data has also information about whether the banknote is legal or if it's counterfeit. Okay, so probably this is one of these groups is the legal one, and the other group is the counterfeit. Okay, but this is a chart. So it's useful to see that instead of trying to analyze the data from 6 variables, we're getting some information that's valuable for with only 2 variables, with 2 principal components. Okay. This is the script plot. This is the script plot, and it shows the variance that's explained by the first component, the second component, the third component, and so on. And there is a rule here that you can imagine this as an elbow, okay? And if you see how this decreases, there's a big decrease here. There's also a big decrease here. But these numbers here, the variance explained by these components, 3, 4, 5, and 6, are very small relative to, even relative to this one, they're very small. So in this case, the rule of a script plot, if you can imagine that as an arm with an elbow, you would place the elbow here, and that will tell you to select 2 principal components.
Okay. In this case, we're like como reduciendo la dimensión.
Yeah, that's what principal component analysis does. It reduces dimension. It's a technique. It's an unsupervised technique to reduce dimension.
In this case, we're just doing dimension 2.
2 dimensions. Yeah, that's right.
Okay.
If we choose only 2 principal components, then that means that we could use these 2 principal components to analyze the data. For example, let's suppose that we are doing regression analysis with some other variable.
Uh-huh.
What you would do is, instead of having 6 independent variables to predict a response, you would have only 2 variables, which are linear combinations of the original variables. But in your model, you would only have 2 variables. Okay. This was particularly important many years ago when the computing power was very limited, and you couldn't deal with models with many variables. Okay, a model with 100 variables, for example, is very hard to deal with. Was very hard to deal with several years ago, And this technique was very useful because instead of working with 100 variables, you could work maybe with 5 or 6, okay, for a regression model, for example.
Can I use principal components in time series or no?
And no, you use it in problems where you have observations that have many characteristics for that particular observation.
Okay, yeah.
When you have, for example, individuals and you measure, you have clinical characteristics of the individual, okay? Or if you have manufactured, let's say, a piston, one of those that they use in the cars. In the piston has many characteristics, has diameter, has hardness, has depth, has what else? Friction, resistance to friction. And so all those characteristics correspond to one individual. And that's when you use principal components, when you have too many characteristics of one individual. Principal components analysis is very much related to also to something called a factor analysis, which we will not cover because that's its main use of factor analysis is in psychology and sociology.
Okay.
But what they do is something similar to principal component analysis and see which variables are more representative in each component, and then they name that component a certain way. For example, they used to measure psychological, they do a bunch of psychological tests, and the respondents have questions that they will answer in a Likert scale, scales 1 through 7. And then they try to group which variables have to do with emotion, which variables have to do with loyalty, and so on, and see if they fit with the different, with the principal components, with one of the components. And then they would call, for example, let's say that the variables that are more related to loyalty are very much represented in the principal component. Then they would call the principal component a loyalty component.
Okay.
And so on. So that's very much what they do, what happens in factor analysis.
Okay.
Yeah.
Thank you.
Oh, you're welcome. Now, how do we interpret these principal components? I'm printing here the loadings. The loadings are how much really each variable is really contributing to each of the components. Those are the loadings. As you can see here, in the principal, you'll see some blank spaces here. By default, this function only prints those loadings that are greater than 0.1. Okay, by default. You can change that default, but by default, it's only the loadings that are greater than 0.1. And what you can see here is that the principal component is really a combination of the inner to lower dimension. You can see the signs here. It's the diagonal times 0.579. This will be the coefficients that come from the eigenvectors. Okay.
This is an absolute value because like these are not greater than 0.1, no? These are negative.
It's greater than 0.1 in absolute value.
Okay.
Yeah. Yeah, I'm glad you asked that. Okay. So here you can see, for example, that if you look at component 1, if you ignore these one that are very close to 0.1, these two are very close to 0.1. What you have here is that the first component is essentially the diagonal, 0.6 times the diagonal minus 0.2 times the inner to upper, and minus 0.7 times the inner to lower. Okay, so that those are the three original variables that most impact in the first component. And in the second component, you have essentially the same variables, but you have a higher weight here. This one is very small, it's minus 0.02. So you could say that the first component is a combination between the diagonal and the inner to lower, and the second component is a combination of the three variables, the inner to lower, inner to upper, and diagonal. The other components, they have also contribution from these variables, but if you're looking at the script plot, we would here decide to go with the first two components to do the analysis. Okay. Because those are the two most informative projections. So let's write down the equations for the transformed variables with the components. Okay. So the first principal component is minus 0.112 x2 minus 0.139 x3. X3 is the right height, minus 0.202 inner to lower, plus minus 0.78 in inner to lower, minus 0.202 inner to upper, and minus plus 0.579 the diagonal. And the second, yeah.
Can you repeat again what you say about the second components and the linear combination?
Yeah, these here, what they're called the loadings, are nothing more than the eigenvectors. And the eigenvectors give you the coefficients of each of the original variables for the transformation. Okay? So when the principal component one is just a linear combination of the original variables, we are ignoring the first one because the loading was less than 0.1. So it's essentially this combination of these other variables. The second component is likewise, it's a linear combination, but now these three variables, because all these three, the first three, we have the loadings less than 0.1. That is coefficients less than 0.1 in the eigenvector. Okay.
Okay, thank you, teacher.
Oh, you're welcome. And the same thing will happen with component 3, component 4. In this case, we decided we're going to work with two components. So remember, x1 is length, x2 is left height, and so on. So we can see that what I said earlier, the first component is essentially the difference between the lower frame and the diagonal, because this one weights very low also. So it's the difference between the diagonal and the inner to lower, okay, the lower frame. And the second component is the difference between the upper frame and the sum of the lower frame and the diagonal. That's essentially what it is. If these were variables related to say behavior, then here we would have, and let's suppose that these three variables were related to, let's say, these three variables were related to sensibility, and the other one to emotional attachment. Okay. Well, here you have a mix. You don't both sets of variables have important representations in both components. So you couldn't call this component sensibility, because there's two elements of this component that are also very heavily represented in the first component, in this first component. Okay. And so if what you do in factor analysis, you rotate you do a transformation, instead of forcing it to be orthogonal, you force it to match something that makes sense for the psychologist or the sociologist. Okay, but it's very closely related to this thing. The presentation is in Brightspace. If there's time, we'll look at it at the end, but normally there's no time to see that. Now, the principal component weights indicate which directions expressed in terms of the original coordinates. That's why it's just a linear combination of the original variables better explain variability. And there's also a measure of how well the first Q components, let's say the first two or the first three and so on, explain variability. And that's given by the relative proportion. Okay, so that's the size of Q for the first Q components with the sum of the eigenvalues. It's the cumulative sum that we saw on the right-hand column and the first table that I showed. Is the sum of the eigenvalues up to Q divided by the total sum of the eigenvalues. That gives me the partial contribution of the first component, the second component, the first two, the first three, and so on. Okay, and this is what we saw in this table. So we can see that here with two components, we have close to 90% of the variance explained. Okay? That's in the script plot confirmed that we need to do that. This is a different form of the script plot. This is the one that we're going to be using a package that does extract information and produces graphs for the principal component analysis, regardless of which function to generate the principal components is used. There are many packages and many functions that generate principal components. And you can see here the script plot that we saw earlier, except that now it's joined, they join this by straight lines, so that it's sort of clear how many components we should take. Okay, here if you look at the relative size of this, that's very small. So we would end up with two components here.
Teacher,
Yeah,
the PC weights are the eigenvalues and those ones, or which ones are the PC weights?
the PC with the principal component weights,
Yes.
those are the loadings.
Okay.
Those are the coefficients. Remember, its principal component is a vector that has as many elements as the original variables. And each element of that vector is the one that's multiplying the original variables to carry out the principal component transformation.
Okay.
And here, this is just the eigenvalues. So this eigenvalue, 2.98, corresponds to this principal component.
Okay,
The
perfect.
second eigenvalue to this one, and so on. Okay?
Thank you, teacher.
No, you're welcome. Now, the covariance between the vector y, and now the vector is my vector of transformed variables, remember. And the original vector x, which is my original variables. If I compute the covariance of that, that's going to be the expected value of x. Remember that we removed the mean from the x to compute the principal components. Okay. So I can just, this is just the expected value of x times y transpose. Remember, we're dealing with vectors here. So the expected value of this vector x times y is expected value of x times y transpose, because that's going to give me a matrix, minus the expected value of x times the expected value of y transpose. Now, expected value of x times y transpose, if you look at your notes from last class, y transpose is x transpose gamma, okay? Minus mu transpose gamma, which is the expected value of this whole thing. And that's the variance, that's exactly the variance of x, the original matrix of variables, times gamma. And that was sigma. Remember, we call that variance covariance matrix sigma times gamma. But we also saw that we can have the decomposition of sigma as gamma, lambda, gamma. Lambda, remember, is the matrix with the eigenvalues. Gamma, capital gamma, is the matrix that has the eigenvectors times the matrix, this is a diagonal matrix that has the eigenvalues, times gamma transpose, and now times gamma. But gamma transpose gamma is the identity because gamma is an orthogonal matrix. The way the principal components are built is such a way that the second component is orthogonal to the first, the third component is orthogonal to the first two, and so on.
So we can say that the covariance between the original vector and the transformed one is just gamma times delta.
Yeah, it's capital gamma times capital delta, which is the vector. This is the matrix that has the eigenvalues, and delta has the eigenvectors, right? This is the this is a eigenvectors, and these are the eigenvalues. And that's the covariance between the transformed variables and the original variables. Now, since this is the expression for the covariance, then the sample, we don't know the actual variance, we don't know the actual correlations, okay? But the sample correlation between xi and which is the ith original variable, and the ith principal component, that variance that correlation is this will be the j. This will be the j. This have to be j. Let me make. I want to make a correction to. This is j. I hope it doesn't take too long. Oops. Okay. So that correlation between xi and yj is going to be from this matrix here, with this multiplication of gamma times the lambda, will give me gamma ij, which is remember the gammas represent the eigenvectors, okay? So it will be the jth eigenvector, the jth element of the ith eigenvector times lambda j, which is the jth eigenvalue, divided by this the corresponding element from the sample variance covariance matrix is xi xj, xi, which is the variance, times lambda j to the 1/2. This is simply gamma ij, the ijth eigenvalue, the ijth element of the eigenvector matrix, times the jth eigenvalue divided by the variance, the variance, and that raised to the 1/2, the variance of the xi of the ith observation, of the ith original observation. Now, these correlations, we use them to evaluate the relationship among the PCs, the principal components, and the original variables. These correlations tells us how they relate, how the principal components relate with the original variables. And in fact, the sum of these autocorrelations, these correlations between xi and xj squared, that sum is equal to 1, because that sum is the sum of lambda j gamma ij squared over the variance. That this is exactly the variance. This is xi, is xi, right? Is the sample variance of the ith original variable. So the sum of these r squares, the correlations squared, is going to be equal to 1. So that rxi yj, we can view this quantity here as the proportion of variance of xi, the portion of variance of xi, which is explained by yj. That's the proportion of variance of the ith variable, original variable, which is explained by the jth component, or the jth principal component.
Is this the same? Is this like the table that we've seen before, that the cumulative variance was 100%?
The cumulative variance is 100%, but this is what this says is slightly different. What we already know that the eigenvalue, for example, the first eigenvalue was explained in 60% of the total variance of all the variables, okay, for all the variables. And here's only relating the ith variable with the jth component. So this is this correlation is telling us what's the proportion of variance of the ith variable, not the whole set of variables, but of the ith variable explained by the jth component.
Okay.
Okay.
So how, in other words, is it how the transformed vector the ith variable of the transformed vector explains the x one?
How the jth variable, how the jth component, this is a component, this is a linear combination of all the variables. Okay?
The component, sorry.
The jth component, how much of the proportion of variance of the ith variable only is explaining.
Of the original one.
Of the original variable.
Okay, yeah.
Okay. And so if theta ij is the angle between, remember, all we're doing is transforming the original space, x1, x2, x6, to a different space, which is y1, y2, up to y6. We're rotating the space of the variables, so that now y1 explains most of the relative of the variables. So when you look at two of the variables, the jth component with the ith variable, these are just vectors. Okay, so the angle between the ith original variable and the jth component, principal component, is theta ij. We're saying that that's theta ij. Then the cosine of theta ij is equal to the correlation between xi and yj. Okay, that cosine is the correlation. And it is a measure of the quality of representation of the variable xi in the jth principal component. Okay, this the cosine of which is the correlation between xi and yj is a measure of the quality of the representation of the variable xi in the principal component yj. And we'll say we'll look at this thing now. This is a chart.
Does this have to do with like a transformation into like angular spaces? Like what is it, the
couldn't understand the question well.
let me rethink it. So does this has to do with the identity circle and how like we're passing information into one space to another?
We're mapping the variables in one space to a different space to capture in fewer variables most of the variability. Remember the case we did with x1 and with two variables. Let me put annotate. Okay, let me do this little drawing here. I have my original variables, and this is x2. And the case where we only have two variables, x1 and x2. Okay, and I have here, this is x1, and this is x2. And my data looks like this, okay? Now, the principal component transformation, all it's doing is changing the axis. And now I'm rotating the axis with the principal components transformation. I'm rotating the axis so that my new axes are now this. Well, I don't have to put it there. Let me put it in a different way. Let me erase this one here. Well, no, but let's suppose that I do it here, because I have to, if I erase here, it will clear all my drawings. And my second axis is now this one. So this will be y1. This is y1, and this is y2.
Okay, okay.
So I'm just rotating the axis. Now, for if I take y1, and which is going to be the new axis, okay, and look at the angle. Now, these are the axes. The principal components will be parallel to this axis, okay? If I take the relationship of y1 with any of the other variables, let's suppose that this is actually my first principal component. Now, this angle here is going to be a measure of how well that principal component is, that variable, how much is that variable contributing to the principal component. If I look at the angle of between these two other variables, if I look, this is y2, right? So if I look at the angle between this and the same data, the same observation, see, that angle is much greater. Okay. So it's a measure because this second component, this variable in the second component is not contributing. There's no high contribution of this variable to the second component. It's contributing more to the first component, this variable. Okay.
Okay.
So looking at those angles, these cosines are the correlations. Okay. Now the correlations, this is a chart I'm going to be using to analyze the correlations, and that's the quality of the representation of each variable on the component. And you can see here that the quality of the contribution of the first variable of inner to lower in dimension 1 is very, very high. You can look at how large that is, because it's remember, these are not the actual correlations. They're going to be the squares of the cosines, in fact. The darker the circle and the larger it is, the stronger or the larger the quality of representation of that variable in this component. So the variable that has the highest quality of representation in the first component is inner to lower. Then there's diagonal. The diagonal measurement has the second in importance contribution to the first dimension, to the first principal component. Whereas when you look at the second principal component, the one that has more contribution is the inner to lower. It's still very light. It's in this range, right? So it's still very light, but if you look at all this is relative, right? So you can say that the largest, the most quality of representation of the original variables is the inner to lower in the first principal component, and the diagonal in the second principal component, in the first principal component also. And there's these three have roughly the same quality of representation in the second component. And notice that all the other squares are in blank, essentially blank. You can hardly see, there's small circles there, but they're almost here. So this is consistent with our original decision to focus on the first two components. Okay, so and this is what we just said, the correlation between a variable and a principal component. We use it as the variable's coordinate in the principal component, and the observations are represented by their projections, while the variables are represented by their correlations, because that's a measurement how much they charge. So each variable coefficient is known as the load. We saw the chart of loadings, and it represents how much the variable is contributing to the corresponding component. Those are the coefficients that come from the eigenvectors. These are the charts that help us understand what's going on with the principal components. This chart is showing, for example, these are just the variables with the first two components by its quality. So we focus here only in the first two components. This is the first principal component. This is dimension first, and this is the second one. Okay, first and second the principal component. And we can see that the inner to upper, the farther they are from the origin, the larger the contribution. Okay, and this, the stronger the blue is, the stronger, the higher the quality. Okay, the color, how dark the blue is representing the how high is the quality of representation of that variable, inner to lower, and in the principal component, the first two principal components, because we have the first two components here. And the farther away they are from the origin, that's the largest contribution. Okay. Now, and this is just the variable contributions to the different principal components. Here, we're looking at the contributions of each of the variables to all the components. Okay, all the components here. We can also look at individual contributions to this is contributions to of each of the variables to the first component. Okay, this is contributions to the second component. This red line here shows the expected contribution if all the variables contributed the same to all the components. So if all the variables contributed the same to all the components, the red dotted line would say what the expected contribution of all the components to each of the each of the variables to the different components. So if you can see, this is the average. We have 6 variables. So if all of them contributed the same, we would have a contribution of 16.66%, which corresponds to this red line. This is for the first component. This is the second component. And now it's the same thing here. Each variable's contribution is expressed as a percentage, and the variables are correlated with components 1 and 2 are the most important to explain the variability of the data. We've seen that before. And the variables not correlated with a principal component or correlated with the last dimensions are variables with little contribution. So these variables here have very little contribution to the components, to the first two components individually, to the first two components. We can also look at the contribution to the first two components as a total. Okay, this is to the contribution to dimensions 1 and 2 to both principal components. And as you can see, this is consistent with what we saw before. These are the 3 variables that contribute the most. These have marginal contributions to the different components. Okay.
So
Yes.
we can take the expected contribution as a parameter into which variables to take in each principal component.
Yeah, you can, and not the main tool that we have to determine what are the principal components is the decree chart. Okay, the decree plot that we saw. That determines we'll stay with 2 components. Now, this you can say you can use this chart, and not exactly the red line is the differences, right? When you look at this big gap here, this is telling you that the contribution of these variables is practically null.
Yeah.
To the first 2 components. So you would you can assume that these are not contributing to the first 2 components.
Okay.
This VR. Now this the way that you compute this thing, the first 2 components contribute to if you want to measure the contribution of the first 2 components of the different variables for the first 2 components, it's just multiply the first eigenvalue for the principal component number 1, the second eigenvalue divided by sum of the eigenvalues. Remember, the eigenvalues are variances. Okay, so C1 and C2 represent the variables contributions to the components PC1 and PC2, and lambda 1, lambda 2 is what we call the eigenvalues. Okay, that's how these the contributions are estimated. Now, let's okay, let's see. Let's take a, it's 10:56. Let's take a break here. Let me pause the record.
Teacher,
Yeah.
Ricardo, I think it's waiting on the, it's in the
Okay.
waiting room.
Okay, let me see. Mm. Maybe it's okay. Thank you. You're right. Okay. Well, in terms of the extraction of these principal components, remember the most important objective of PCA is to try to work with the smallest number of components possible. Okay, that explain most of the variability in the data that we have. Now, since they're ordered from the one that explains the largest amount of variance to the one that expresses represents the lowest amount of variance, we need to focus only on the first ones, on the first few principal components. Those are that explain most of the variance. Again, the script plot is a very useful device, but there's sometimes that somebody, an expert in the area, sets a minimum percentage of variance that needs to be explained. And then we will have to go with that rule. The eigenvalue we saw that it's a variance, as a measure of the variance that is explained by its corresponding component. And an eigenvalue of 1 represents the variance of a single variable. So that we have p variables, we have p eigenvalues, and we will have p eigenvectors. Now, I'm going to do one exercise here with R, and then you'll do this one with the Wisconsin breast cancer data. Okay. In Brightspace, you have the description of the data set. And at the beginning, ignore the result of diagnosis. Diagnosis is this data set. We will also use it for prediction. So we will use it also in supervised learning. But now ignore the response until at the end of the analysis. And what you'll do is something similar that I'm going to do now here with you in R. Okay, so please, I updated the scripts. So this script AM03 _1 that says ACP simulation, which should be PCA simulation. This one's still in Spanish. You can read that script. Here in that script, what I do is I go step by step computing the eigenvalues and the eigenvectors using matrix multiplications and vector multiplications and so on. So it's going through the basics. You may want to be interested in following the script. I don't want to spend the time here to do it, because essentially what we saw in the theory, just put it there with simulated data in the script. So I will not go over that one. But there's another one that's called AM03 _2 _ACP Swiss bank notes. And that says Inc, but that's already translated into English. And that's the script I'm going to be using. Okay. That's the script that I'll be using. So please download the script to your computers. And again, it's AM03 _2 ACP Swiss bank notes, which I didn't change the name. Okay, and once you unload it, here there's some things I wanna note here for you. So just unload it and then install the packages, and we'll go back to some of the comments that I have there. Install all the packages and set your working directory wherever you have your data for the this is the Swiss bank notes. Okay, I'm going to be running the thing. So I've run all those package installations from line 30 to line 47. And then we'll go over since the beginning for some comments that I have there. That's important to know. Okay, assume that everybody's already with the script and have installed the packages. Some of the comments I make here is are important for you to know. Let's see, like one scatter plot. Okay, we will do the performance, the PCA on the Swiss bank notes. We will show the first components and scatter plot, and we will also see the script plot, which what was in the presentation. Okay. Now this is important. Different packages do the matrix decompositions in different ways. So that can yield to different eigenvectors with possibly some some different the signs of some of the coefficients changed. The end result is going to be the same, regardless of which package you use, but just need to be aware that if you use different packages, the plots may be different. The plots that you see, the first principal component may be plotted in the y-axis and the second one in the first, and so on. So there are some minor differences. The important thing is the final result is the same. Now, to perform PCA, principal component analysis, we have these two functions, prcomp and printcomp. These come with R. These are functions that come with R. There's a package called the factominer, and the function to the principal components there is PCA. And for that factominer package, we'll be using that factominer. The DoDi.pca is a package called ADE4, and EPPCA is a package called exposition. Okay, we will be using either the printcomp or the function for factominer. Factominer has the advantage that you can, regardless of which package you use to extract principal components, the factominer has very nice functions to do the plots that we saw in the presentation. Okay, so once you install the different packages, I set my working directory and so on to where my data is. I set this ggplot2, although it only takes, the package has its own graphics, the factominer package, and doesn't respect some of the things from the global. I erased the whole thing instead of doing Control Enter, I did suppress. Control Enter. Now, remember the files Swiss bank notes is tab separated, so we're going to read it. And remember, we've read this file before. We have the length, the left height, right height, inner to lower, inner to upper, diagonal, and counterfeit. I'm going to put in an array in a data frame called SVNX. I'm going to set SVN, and I'm going to remove the last column of the original data frame, because the last column has the information of whether the node is counterfeit or is it legal. We don't need that now. For now, it's unsupervised learning, so in theory we didn't have to have that. All the variables are treated equal. Now, we saw that one of the assumptions to do PCA is that we standardize the variables to get rid of big differences in units of measurement. To do that, you can use a function that we will not be using now, because the variables are very similar. Now, the first thing we check is the level of correlation between the variables, right? So the SVNX, yeah, only has the variables without the counterfeit information. I haven't run that line. SVNX has the variables without the counterfeit information. First, we compute the pairwise correlations. So we use the function core to compute the correlations, and I'm going to round them. I'm going to round them to decimal places, and here I have the correlations. This is the correlation matrix. Let me expand this thing a little bit so that everything falls in the same line. Okay, I have all the correlations here. Again, we can just look at these numbers and see if we find that this is a small number of variables. So we can, from these numbers, know which, if one variable is not related at all, not correlated at all with any of the other variables. There's another function that's useful, and it's a function to compute the p-values of if you were to test the hypothesis that the correlation between xi and xj is 0 against the alternative that it is different from 0. To test that hypothesis, I can use the core pmat, that's the p-values matrix, of the original data. Okay, that's SVNX.
I have a question.
Yes.
SVNX, what variable, what is it taking, or what is it?
SVNX is the same as SVN, except that I'm not including the last column.
The last column?
SVN is what I read the data, Swiss bank notes in SVN. Now, here I have all the variables, including the counterfeit column, which is the last column. I'm removing the last column. Okay, so here it doesn't appear. When I look at the names of SVNX, it ends with diagonal, which are the 6 variables. I don't have the counterfeit variable because it doesn't make sense to include the other variable in the correlation, the computation of the correlation matrix. Nor it makes sense to include it for the computation of the principal components, because that's a binary variable. And remember, principal components assume that the variables that we're using are all continuous. Okay. Now, so I'm going to compute the p-values, set it here in p-val. And if I list p-val, these are the p-values for the different tests. For example, this is a p-value of the test that the correlation between length and, I'm sorry, this. Of course, in the diagonal, it only has zeros. There was doesn't make sense to compute the correlation. Correlation between length and length is always 1. So it's definitely very significant. But for example, the correlation between length and left height the p-value is very small. So we could reject the hypothesis that the correlation is 0 against the alternative that it is different from 0. However, when I look at the p-value for the inner to upper, it's very high. The p-value is 0.38. So I could not reject the hypothesis that the correlation between length and inner to upper is equal to 0. Okay, so it's not significant correlation. Now, if I had one variable with values greater than, say, 0.1, 0.2, 0.3, with all the other variables, I could remove those variables because they are not correlated. I mean, statistically, they are not correlated with any of the other variables. This is not the case here. All the variables have some sort of correlation. Here, I have several p-values which are very small for all the variables. So we visualize the correlation matrix. We use the library is a ggCorePlot, and I use the function core. This is the graph that you saw in the slides. This is the variable, the correlation plot for all the pairs of variables. Of course, in the diagonal, As there is red because it's 1, the correlation is 1. Okay. Now we can plot only the upper diagonal. I use the same function, but I note the parameters here. Type equal to upper, then it's going to give me just the upper diagonal. And I put the matrix here, and let me change the matrix, correlation matrix. Swiss bank notes. Okay, that's a correlation matrix. I have an alternative visualization with the library gggali. Here I can change the palette. The palette is the range of values of colors that's going to be using. ggcore, I told that the palette is RDBU. If you want to check which palette you have available, you go to Google, say color palettes in R, and it'll display the different color palettes that you can use. So this is just displaying the lower diagonal, and colors go from this blue to this red here. The almost white will be very small correlations, and as you can see, I don't have any case where I have very small correlations between a pair of variables. Okay, so the first assumption then holds. I have the correlations. There's no single variable that has 0 correlation with the others. I can use this ggpairs function to visualize density estimates and the correlations. You also have this thing in your slides. That's with the ggpairs function. Okay, it's useful because it gives you also the density estimation of the data. And thanks to this, we could notice that there's a bimodal density that corresponds to the diagonal measurement. Now, what I was saying earlier, if you had to standardize the variables, you would have to use the function scale applied to the data frame. We don't have to do it here because the scales, if you look at the summary of the data, there's no huge differences in scales. Okay, you have, for example, medians are around 214, 130, 130, 9.1. I don't have any case where a median is, say, in the tens of thousands, and the rest are in the 300s or 200s. Okay, so I don't have a huge difference in scales, so I don't have to use it here. We're going to use the function printcomp. Let's look at the structure of printcomp. Printcomp is to do the principal component analysis. This is the basic. This comes with R, with the stats. Okay, so this is not the function from the package factor extra. And it tells you here what are the elements that you have to consider. You supply the data. It tells you here what the data is, what sex, and so on. Okay, I'm going to do it here. I'm going to say printcomp of the matrix SVNX to compute the principal components of the matrix. Okay, now let's look at the structure of this object, which I call CP, because I didn't translate the whole script. CP was for components principales. It tells me that it's a list of 7, has a component called standard deviation, is div, loadings, center, scale, and ops, and scores, call, etc. All these things, I put the meaning of all these things here. SDEV is the standard deviation of the principal components. Okay. The loadings is the matrix of variable loadings. That is the matrix whose columns contain the eigenvectors. Okay, that matrix has the eigenvectors, loadings. Center is the means that were subtracted from each variable. Remember that to compute principal components, we always subtract the mean, so that the mean of when we do the principal component transformation, the data is already has mean 0 in all the variables. Scale is the scaling factor applied to each variable. In this case, the scale will appear to be 1 because we did not scale the variables. A number of observations, NOPS is the number of observations, and scores. Here, if scores equal true, which is the default, by the way, these are the scores of the supply data on the principal components. Okay, and this is an object of class loadings. These scores are an object of class loadings. We'll compute the. Let's look at these elements of the principal component structure. Scale tells me it's only once because I didn't scale the variables. Center tells me what was subtracted from each of the variables to center it, so that it had mean 0. The loadings are what we saw in the presentation, and these are the vectors of the principal components 1, 2, 3, 4, 5, and 6. Okay, it gives me the sum of squares of the loadings, the proportion of variance, and the cumulative variance. Okay. Now, I'm going to say here structure of CP scores. And it tells me that the structure here is it has 200 rows by 6 columns. Remember, we had 200 observations, and it just tells me for the 200 observations what are the transformed variables: the component 1, component 2, component 3, component 4, 5, and 6. So each value in the original matrix is transformed with that linear combination, and I have that matrix here in loadings. Now, there's a function called loadings. And you see here, loadings is, it takes an object of class fractanal or printcomp. It's a result of a principal component analysis. Then digits the number of decimal places to use in printing uniqueness and loadings. The cutoff is the loading. I can change the cutoff of the points, and I can sort them. Okay. Then by default, it is sorted by from the largest to smallest. Okay. Now, let's visualize the result. To visualize the results, we're going to be using this package FactoExtra. First, we obtain the eigenvalues with the percentage of variance explained by each of the components. Okay. So if I say now get eigen CP, that gives me the same thing I saw in loadings, right? When I displayed loadings, because it's the eigenvalues with the variance explained by each of its corresponding eigenvectors. Okay. So I use this function get eigen CP, and that's what it gives me. Now, to visualize the functions in FactoExtra start with an FVIZ. Okay, to visualize the information of the principal components. So I'm going to visualize CP, and that gives me the script plot. Okay, so if I just say FVIZ IG CP, this gives me the script plot. I can change the colors and everything here with the different parameters. Okay. Here, in terms of choice, I'm telling that it has to give me the variance, the eigenvalue. Okay. Geom is going to be a bar. I use bars for each of the eigenvalue, for each of the variances explained by the eigenvector, and join them by a line. A bar field, I use the steel blue. It's going to generate exactly the same graph. I can put it just blue. Bar color, I'm going to say blue also, and line color black. Number of components. I'm going to it's not going to. I'm going to say 10. 10 is the default. Okay, 10 components is the default. If in this case I don't have 10, I only have 6, so it's going to display 6. Okay. Add labels equals false, and h adjust equals 0. It's not going to make the adjustment on the height Okay, so I just changed the color and the rest I left it the same. Okay. You can use the defaults or you can change the defaults here. Now, get PCA int and get PCA var are functions to extract the results for individuals and for variables. Okay. If we have a huge data set, doing it for individuals is just going to give you very confusing plots. Okay. We'll try it here, but it only gives very confusing plots if we have too many data points. So we get the information for variables or for individuals with get PCA int. Now the coord contains the coordinates of the variables to generate the plot. Okay, coord. Coord contains the correlations between the variables and the dimensions. The dimensions are the principal components, okay? So these coord are the correlations between the variables and the dimensions. Cos2 is the quality of representation of the variable in the map of factors, and that is the square of the coordinates. Remember, the cos2 is the square of the cosine of the cosine. Okay. The contribution is the contribution in percentage of each variable to each of the principal components. And it is in percentage, okay? So it's essentially cos2 times 100, the one that we get from here, divided by the total components cos2, because cosine squared. And to visualize the quality of the representation of the variables in each component, we use the function coord plot. Okay. Now it's the same function we used earlier, the coord plot. Now I'm going to call var CP. I'm going to get the information for the variables of the principal components using the function var PCA var. And I'm getting the variable information. Okay. With the get PCA var, I obtain the variable information. Now let's look what this structure has. It has coordinates, which I listed here, a coord, which are the correlations, cos2, the square cosine squared, and the contribution in percentage of each variable. Okay. So I have that, all that I have in this structure, variance in var.cp. Now I'm gonna use I don't have to load the library again, but anyway, the coord plot library, and I'm gonna do a coord plot of the information for the variables, but I have to put it here. This is not a correlation matrix, so I have to indicate coord plot that this is not a correlation matrix, okay? Because by default, coord plot is for correlation matrices, to plot correlation matrices. I plot this, I don't know what happened here. There's this one. I don't know what's doing here, this thing here. Let me see, graphics. Coord plot. That's the coord plot that we saw in the presentation, okay? And remember, this is a cosine squared. I'm doing the coord plot of cosine squared, and that's a measure of the quality of representation of each of the variables in the principal components. And we already noticed here the sizes of the circles and the colors indicate the quality of the representation. That's one way of looking at that. We can also plot the variables in different colors using the argument cos2 as to determine the color. Okay, so the quality will determine the color of the representation. And for that, I use the FVIZ visualization, the last of the variables. I use color, col.var equals cos2, and repel equals true, so that the the names repel and don't overlap. Okay. And that's a graph. So the repel, what it does is it makes sure that the names that I plot here that are shown in the graph are not overlapped. That's only all it does. So as you can see, cos2 is goes from 2 and to 0, and it's a measure of the quality of representation. Here's the diagonal. Okay, diagonal has the highest quality of representation, as we saw it in the previous chart. Okay, and the distance to the origin shows the size of that representation. Okay, that's the first principal component and the second principal component. So this is the graph with the first and second principal components. Now we can also change the transparency. We can use color bar equal cos2, but we can also use an alpha bar, which changes the transparency of the line using the variable cos2. Okay. It's very light, very small difference in how we say it now. Okay. But you can use that range of values for the transparency. Now the variable contributions, let's look at the variable contributions. I'm going to round them to 2 decimal places. So here the contributions to dimension 1, dimension 2, dimension 3, principal component, second component. I see all the numbers here. I'm not omitting any number here. And remember, when we displayed the loadings, this one didn't show. Okay, but these 3 showed, and these 3 didn't show either. Here I'm showing everything. Okay? All the coefficients. So in fact, the principal component number 1 is going to be 0.19 times the length plus 1.26 times the left height time plus 1.94 times the right height, and so on. Okay. Now let's look at let's plot the contributions. Let's do the core plot of the contributions, and that's the contributions. That's essentially looks like a script plot, but it's showing their contributions related to this mid-level, which will be the expected contribution if all of them contributed the same. That's for principal component 1. Now I'll do it for principal component 2. And that's the second chart you have in your graph. And I'll do it for the first 2. So for the first 2, I do axis equals 1 through 2. Okay. Contributions first to 2 principal components. And that's the plot that you also saw in the presentation. Okay.
Teacher, I've been having trouble with the function. I've been having a little bit of trouble with the functions.
It's not working, or?
Yeah, the fits PCA var function, it's not working.
I have the same problem.
Okay.
I have a problem, but when it comes to the graphs, not this ones, but the previous ones.
Okay. Any of you want to share your screen to see what's going on?
Sure. So I load the package for Factor Extra, and like this is okay, but when it comes to the function, it tells me that there is no package called car.
Again, let's see. I see variance geom, bar fill, still blue, bar color, and color. Add labels, false, it's just. That error, it gave you the error when you say fbs_I. See,
Yeah,
and
right here.
Okay. Could you please say structure CP, STR CP? STR, it's only STR,
Okay.
CP. SDEV loading, center, scale, knobs. That's fine. FVs, that's weird. Let me check if I use exactly the same. Viz underscore I CP. That is weird. Because it's exactly the way I run it now. Error in load namespace.
And you see the,
Okay, load car. I don't know. Try to load a package called car. Go
I
to
have a package called card data.
no, but it tells you for another package car. Let's try to load the package car and see.
Should I
Go
load it
to-
up?
You can go to tool to. You can
Tools,
go
then
in the menu to. Okay, here stuff from procedure car. So it's all lowercase. That's it. And now say library car. And run the FVs again.
let's see.
When you loaded the package, did it give you an error? Oh, there is an error. It gave you an error in library car. It says there is no package called car. When you install it, go a little behind in your console to see if it gives you an error when you install car.
Can I what?
In the console, where down and to the down left panel, go a little bit up. Let me see when you install the package car. Oh no, it had a problem loading the package car. Had non-zero exit stats. What's the version you're running for R? For R?
It is, wait.
You can see it in global options.
This is 1.1463.
Yeah, R Studio, but to the version of R, just go to global options to see what the version of R that you're using. In the menu, there's a thing called global options.
In the menu, file, open. In file or
You,
RStudio?
I guess you hide it. Your menu is hidden.
Oh, all right. Pero, like, ¿en dónde lo? Es que no lo entiendo.
See, if the menu is in the top part, there is a menu. I don't know how you hid it, but it's a menu that says File, Edit, Code, View, plots, session, build, and there's something tools, and then you go to global options,
Ah, yeah, sí.
okay? And look at R.
Uh,
No,
Can
it's
you-
it should be shown. Let me tell you what you should have there. You go to global options. There's something called R general, and that has to show the 64-bit R 4.1.1.
like I have a default working directory and it like gives me the browse thing.
No, but it doesn't tell you the version of R that you're using. That's
No.
weird. In general. Let me open my menu. Let's see.
Okay.
Tools, global options. In R general, there should be two blocks. One that has the R version, and the other one is the default working directory. So let me see again what. That's weird because it should show you two blocks. One for the version of R that you're using, and the other one for the default working directory. No, do cancel and then let's go. Let's reopen. No, that's going to be a waste of time. Let's try again with the tools, global options, and see if it shows the right menu. I'm not sure what's going on. No, it's not showing you the right menu. You're going to have to restart RStudio.
RStudio? Okay.
You have to cancel that session and restart it. The other people that had problems here, is it the same problem?
No.
No?
No.
Okay. Can you stop sharing so that somebody else can share their problem, see what's going on?
Yes. In my case, let me show you. It appears this problem.
Okay.
This one. Que dice error in repel boxes. And que dice no ofrece la función RCPP.
It gave you after you run the remove the repel. It's gonna probably overlap some labels, but just remove the repel equal true.
Okay.
Yeah. Remove it.
Let me see. Yes, it works.
Yeah, it's overlapping the labels. Now it's weird that it didn't give you repel boxes, data points equal as matrix data. Okay, the recipe should remove no first set of function. And let's run that one with the repel.
Okay.
182, line 182. Now it's taking too long for some reason.
Yes, I think that is like getting to a loop because.
Yeah, it's not working.
Yes.
Okay, let's, if you can send me the error message that it sent you.
Okay, yes. Can I send you this in the chat here?
Yeah, you can do it.
Okay.
Okay. I'll check it later in Google.
Okay, thank you very much.
Okay. Anybody else?
Yes, I also have a problem. Is it okay if I share my screen?
Sure.
Okay, 2 seconds. Yes. Okay. So here I get like this error that says that the viewport has 0 dimensions. I really don't know what it means. But it's funny because this is the only graph that I have been able to get, but the previous ones I haven't.
Plot. To avoid text margin, please try again with a clean new empty window. Okay, let's try do a graphics dot off before any of the charts that you couldn't generate. Go to the first chart that you could not generate.
I think it's from the very start.
Okay.
Here, I think it is.
Do before that, put
Yeah.
graphics dot off. That's it. Control Enter. Now if this.
Yay! It
Okay.
works. Yes,
Now,
thank
just
you.
the other thing is you have very short plotting area. That will
No,
give you an
yeah.
error sooner or later. Okay.
Yeah, I know. It's because I was like having 2
Okay.
screens at the time.
Okay.
Yeah,
Okay.
thank you.
Oh, you're welcome. Okay. Anybody else? Okay.
Should I just quit and then reopen it?
Mhm.
Or still?
Did you reinstall all the packages?
Did I what?
Did you install again the packages? Okay. You're running. What are you doing now? You're running the script. That is?
Yeah, I'm trying
Okay.
to again since the beginning.
Can you share your screen?
Yes. Wait a second.
Sophia, could you also try a device off before the chart that you could make now with the repel?
What?
Try also graphics.off,
Okay.
open and close parentheses, and run the first function and adding the repel equal true.
Okay. Graph.
That'll work. Farid, can you just select everything, all these lines until the line where you had a problem and run it? Because you had a problem in that one, no? No, the same error. Now go to your global options. Global options, and then no, it's still not showing you. No, what you're gonna have to do, you have to reinstall RStudio. So there's a problem with RStudio. because it should show you the two windows, okay? So you have to reinstall RStudio and make sure that you're running the last version of R, which is the 4.1.1. Okay? And but that's going to take some time. So let's go on with the script, and then now that you do the exercise in Teams, somebody else can do the script, can run the script. Okay. So let me continue here with the script. Let's okay. Now this biplot generates a plot of individuals and variables, and you'll see that when you have many individuals, it's very difficult to read. I mean, if we had here, we only have 200 cases, but all this is telling you is which of these individuals or observations are more loaded to one of the quadrants in the new space, okay? And you can see here the separation between these two groups. And we'll see later that this separation corresponds to the counterfeit and the non-counterfeit nodes. Now structure, but let's look at the structure of counterfeit. It has zeros and ones, okay? We'll make it a factor. Now I'm going to use the information of counterfeit, which is zeros and one. I'm going to make it a factor. And I'm going to do a graph of the principal components individuals. I'm going to use points so that they don't show the text. It only shows the points. Call int, I'm going to use the counterfeit as the color. Okay, I'm going to change the color of the dots depending on whether the variable counterfeit is 0 or 1, that is if it's legal or counterfeit. I'm not going to add ellipses. You can add sort of confidence ellipses here. I'm not going to add them now. And I'm going to use the legend title for legal and counterfeit. Okay? So I show this graph. And as you can see here, the first two principal components are giving me a pretty good idea of how to separate the legal versus the counterfeit bills. Okay, these are the legal nodes, and these are counterfeit. So just looking at the first two principal components, you can now you could use this information to do supervised learning and build a classification algorithm for legal and counterfeit. We'll see later that that's not the best thing to do, because principal components don't consider the response. So when we have supervised learning, there's other methods that we should use instead of these principal components. Okay, but you can see clearly here that the first two components do a pretty good job in separating the legal and the counterfeit. I can use the defaults. Okay, I can. I'm going to do a SVN counterfeit. I'm going to recode. Counterfeit 0 is, I'm going to call it legal. 1 is going to be counterfeit. I'm just going recoding the values. Okay, and I'm going to do the chart. And I show the ellipses. Okay, I add ellipses equal true, and I have a legend here with legal and counterfeit, and that's it. So instead of listing 0, it lists legal, and then instead of a 1, it puts counterfeit. Okay, so that's the ellipses that the sort of say where most of the data points fall around the center, which is this center of mass of each of this set of points. Okay. Now, what I want you to do is I'm going to split you in groups. You'll take the break now, and we'll come back just to review the results. And you're going to do the exercise with the Wisconsin breast cancer data. Wisconsin breast cancer data is, let me see, it's a file called, let me go to the data sets. It's Wisconsin breast cancer. Okay, that's the Wisconsin breast cancer data. It is a CSV file. Okay. So it's a file, a text file separated by commas, and that's it. That's the file. The first line has the names of the variables and so on. So you use that data set instead of download that file to your computer, and you're going to follow the steps we did now in the script. You're going to follow the steps, do the analysis, the principal component analysis, to produce the graphs and all that. And at the end, just add the variable that has the response, whether it's breast cancer or not, okay? The diagnosis. That diagnosis variable, remove it at the beginning and do the analysis with all the other variables for the principal component analysis, and then add the diagnosis to see if we see something similar to what we saw with the Swiss bank notes. Okay, so I'm gonna stop sharing. I'm gonna allow everybody to share. Okay, and I'm gonna split you in groups. So take the 10-minute break if you want first, or take the break at the end. It's 12:10, so we'll come back 20 minutes before, well, 25 minutes, 12:35, 12:40, so that at least one of the teams shows what you got. Okay.